Whoa, I've only bloody gone and hit 10k. Thank you so much for being here. You lot are the absolute best. Somebody get the champagne. To celebrate hitting 10,000 subs, I wanted to make a video running through the 10 most important climate topics to watch out for. So I asked my fabulous Patreon gang which topics that they thought I should cover, and this is what they said. So in this video, I'm going to take you through oceans, climate modelling, uncertainty, clouds, climate sensitivity, committed warming and sea level rise, tipping points, false solutions, bad actors, and activism. And if you want to be part of the conversation next time, you can join the crew over on Patreon. All right, let's jump in. I'll be the first to put my hands up and say that I don't give the ocean enough airtime on this channel. Blame my meteorologist bias. But this year, the ocean has forced its way into our attention and into our newsreels. For more than an entire year, global sea surface temperatures have been at an all-time high, blowing records, if you'll excuse the pun, out of the water. Since May the 4th, 2023, ocean temperatures have soared, breaking records by a huge margin. And before you mention it, it's not just down to El Nino either, because temperatures are high in almost every one of the world's oceans. But it's not just the surface we need to be worried about, because deep ocean heat has been increasing too, including some of the areas most crucial for driving global ocean circulation, like the North Atlantic and Southern Ocean. Oceans absorb almost all of the extra heat kicked out by human activity, a massive 90%. And since the early 1990s, so pretty much my entire lifetime, that heat uptake has increased dramatically. In fact, between 1971 and 2018, the world's oceans absorbed an amount of heat energy equivalent to 25 billion of the atomic bombs dropped on Hiroshima. Much of that is concentrated in the upper layers of the ocean, but new research suggests that heating below 700 meters is rapidly increasing too. All that extra heat has consequences. A hotter ocean takes up more space, adding to sea level, and a warmer ocean also melts more ice, also adding to sea level. And especially nearer the surface, a hotter ocean contributes to the kind of marine heat waves that we saw around the UK last year, and puts stress on vital ecosystems like coral reefs. And of course, it would be remiss of me not to mention that warmer ocean temperatures were one of the primary culprits in last year's record-breaking lows in Antarctic sea ice. Sea ice is a really telling indicator of the state of our climate. Arctic sea ice has been in a state of decline for decades, plummeting closer and closer to an ice-free summer. And there are signs that southern sea ice is going the same way, shifting into a new low sea ice state. One of the reasons that sea ice and ocean temperatures have taken scientists by surprise recently is because it's so outside the range predicted by climate models. But what's a climate model, I hear you ask? Only my second big topic to watch out for. Climate models are such an important and poorly understood tool. They range from the simple theoretical thought models that were developed in the 1800s to think through what would happen if we doubled or quadrupled atmospheric CO2 concentrations, to the colossal computer code monsters of today that scientists, including me, run on supercomputers to understand the planet. Models have many different purposes. For instance, we can run models to explore specific events in recent history, like an atmospheric river or a heat wave, for example. This is especially useful if you want to see what caused an event or to understand the impacts. Models are also super useful in areas where we have limited direct observations, like the Antarctic. We can use models to understand distant periods of time too, like many millions of years ago or many decades into the future. Or we can use them to predict the weather a week or so in advance. And in fact, this is probably the use you're most familiar with. Regardless of their use, modern weather and climate models all share the same philosophy, but they're also pretty misunderstood. I used to think of computer models like a black box, and I had no clue how they worked their magic. After nearly a decade of working with them, I now like to think that I have a good idea of what the box contains, so let me open the lid and let you peek inside. At their heart, climate models are just maths. Scientists have gained a lot of knowledge about how the world works over the last centuries, and we can describe most environmental processes using maths. whether that's how the wind blows, or when a cloud forms, or how water moves in the ocean. Models are just very sophisticated calculators, performing millions of calculations every second to predict what conditions will be like at a given time after we start them off. If you're interested in predicting the weather, you're going to want to know the temperature and whether it's going to rain in the next 24 or 48 hours or so. So you'll tell the model what the weather is like today, and off it goes, doing its maths to give you the answer. If you're interested in predicting the climate though, you'll have a longer term perspective, so you might be less interested in the day-to-day changes and more interested in the changes that are decades or centuries ahead. So you'll tell the model what the temperature and CO2 concentrations are today and how you think that they might change and develop, and then set it off, and off it goes, doing its maths to let you know how the average climate will change in response to the scenario that you've asked it to predict. Whatever specific task we use them for, models are a great tool to understand the past, present and future. And climate models have actually done a really good job of predicting current climate change, especially when it comes to average temperature rise. But of course they are only tools, and there is still a lot we don't know, especially about how our actions will change in the coming decades. And that uncertainty is a fact of life. Which brings me to my third topic. Because, the more you know you don't know, Uncertainty means something quite different in science to the way that we use it in our everyday lives. In an everyday sense, being uncertain means we're not sure about something, which in the context of predicting the future seems like it could be a problem. But scientific uncertainty refers to the range of possibilities. Let's think about temperature, for example. Any measurement of temperature comes with uncertainty. If you're squinting at the lines on a thermometer, can you really tell if it's 20.1 degrees or 20.2 degrees? The precision of the instrument means that there's always a little bit of wiggle room either side of the most likely value, giving a range. In this example, it might be 0.1 degrees either side, but all instruments will have a measurement sensitivity range. This range is one type of uncertainty, but things in nature are also not always exactly the same, even under identical starting conditions. For instance, the exact same amount of solar energy might result in a slightly different temperature in different weather conditions. Uncertainty also accounts for this natural variation. So if we're making predictions, uncertainty tells us about how confident we are in our results. We know what the most likely value is, but when we report a range, it means the true value could be anywhere within that range due to natural, random variations or the precision of the methods used. That's why using multiple different methods to predict or observe the same thing can reduce uncertainty. And speaking of uncertainty, clouds are the #1 source of uncertainty in our projections of future climate change. Clouds can act like a blanket, trapping in heat, or like a mirror, reflecting it back to space. That makes them an important planetary thermostat that can control how much energy reaches Earth's surface and therefore its temperature. But it gets complicated because how clouds affect the planet's surface depends on their properties. And there are a lot of them. Things that matter include how much liquid is in a cloud versus how much ice, the height and thickness of the cloud, its temperature, how big the individual particles are, their shape, the number of small versus large particles, the list goes on and on. All of these properties affect the energy reflected from or trapped within the atmosphere in different and often competing ways, which makes it very hard to nail down the exact impacts of clouds on the surface. Plus, they're very difficult to observe. Firstly, they change very quickly. Just think about how fast a hippo in a cloud turns into a tortoise or a man holding a cigar. They're super high in the atmosphere too, meaning we have to fly through them somehow to measure them, which is difficult, dangerous, and expensive. And they present a multi-scale problem because they cover vast areas of the planet, but what controls their impacts at the surface happens at the micro scale. So despite huge advances in our ability to simulate clouds with climate models, they remain a key question mark in our projections of future climate change. The uncertainties in clouds are one of the main reasons we still have a poor understanding of climate sensitivity. Climate sensitivity, or more precisely equilibrium climate sensitivity, describes how much Earth's temperature rises in response to a doubling of atmospheric carbon dioxide concentrations. And it's important because if the climate is more sensitive to greenhouse gases, the impacts of our actions will be even more serious, and a smaller amount of human activity could push the climate system even further into dangerous territory. So what happens if we chuck twice the natural amount of CO2 into the atmosphere? I'd love to give you a precise answer for that, but annoyingly, it's a stubborn number to pin down. Estimates basically haven't changed since it was first introduced as a concept in the 70s, and the most recent IPCC report pegs it at 2.5 to 4 degrees Celsius. This isn't actually that different from the range of 1.5 to 4.5 degrees that Jules Charney and colleagues came up with in 1979. The range hasn't narrowed much, despite huge progress in our understanding of the climate, because there are still question marks about important feedbacks in the climate system, especially relating to clouds. The more we observe our climate, the more we learn about feedbacks and about tipping points that can cause abrupt change. But hold that thought, because we'll come back to those later. The main message, though, is that while scientists may disagree about the true climate sensitivity, we know in the simplest terms that it's positive, meaning that greenhouse gas emissions increase global average temperatures. That's evident from the climatic change we've already seen so far and has been established using many lines of evidence, including historical observational data, proxies from prehistory, and model simulations. One reason that climate sensitivity is important is because knowing how our planet will respond to our actions will help us adapt to the consequences. Our actions have already caused serious, long-lasting changes to our climate, but some changes are still in the pipeline because certain parts of the climate system, especially ice sheets and sea level, respond much more slowly than others. So the question of how much is already baked in is a very good one. But the answer depends on which impacts we're talking about. First, let's think about committed warming. If today's concentrations of greenhouse gases were kept exactly as they are today forevermore, which is entirely unrealistic for reasons I will explain in just a minute, then it would take a long time for the climate system to reach a new temperature balance. In this constant atmospheric composition scenario, we'd be committed to warming of 0.3 to 0.9 degrees C. But keeping the composition of the atmosphere constant is a totally bonkers concept outside of model world. Can you imagine the world emitting just enough CO2 to compensate for the oceans and trees and salt marshes of the world absorbing greenhouse gases? No, it works in a computer model, but is absolutely not designed to be a realistic experiment. This scenario is what people often confuse for committed warming, i.e. the warming that is inevitable because of our past misdemeanors. But actually, if we're concerned only with what our past actions have locked in already, then we should be thinking about what would happen if we stopped all emissions tomorrow. Granted, another unlikely scenario. Lots of recent research has shown that if emissions stopped completely, temperatures would actually stabilize or begin to reduce quite quickly, which means that committed warming from a physical science perspective is actually basically non-existent. The only thing that is locking in future warming is our current political, cultural, and socio-economic situation, and the emissions inevitably associated with that. Now, obviously, we are not going to be able to completely stop emissions overnight, and there is a degree of inertia in the amount of committed emissions from past and present policies. But it does mean that any actions to reduce emissions will have an immediate impact on temperatures, which is really great news. It means we still have agency in the matter. However, temperature is not the only thing we care about, and one area where we are locked into some future change is sea level rise. That's because ice sheets, and especially the big ones in Greenland and Antarctica, respond very slowly to temperature change. The ice sheets are losing mass as a result of rising atmospheric and oceanic temperatures, and this would continue even if warming stopped tomorrow, simply because it takes ice sheets so long to catch up with climate changes. And that's before we get to to tipping points. If you've seen some of my recent videos about West Antarctica, you will know that we are probably in for a lot more sea level rise if certain thresholds are breached. And we still don't know for sure where the tipping thresholds for the West Antarctic and Greenland ice sheets are, or even how we would know if we'd passed them. Ultimately, the differences between committed warming and committed sea level rise just come down to how fast the systems respond. Atmosphere quick, ice sheet slow. Okay, I've mentioned them enough now. Time to give tipping points some proper airtime. Committed warming and sea level rise both depend on tipping points because they will impact how fast and how far the climate will change. A tipping point is a point beyond which change becomes irreversible on human timescales, also known euphemistically as a high impact, low likelihood event. It could be the collapse of an ice sheet, or the loss of the Amazon rainforest, or the shutdown of an important ocean current like the Atlantic Meridional Overturning Circulation, or AMOC. We know that there are some critical tipping points in the polar regions, and for a summary, watch this video next. Tipping points arise because of reinforcing feedbacks that accelerate change, like the loss of sea ice or the thawing of permafrost. There's still lots to learn about these processes, primarily because we've not got much to go on. We've never seen them in action before in our previously stable climate. Most of our evidence about tipping points comes from paleohistory, for which we only have indirect evidence. For example, we think that there were rapid jumps in sea level associated with ice sheet collapses after previous ice ages, known as meltwater pulses. We can learn a lot from these historical events, but there's still lots we don't know. For example, how long do we have to spend above the tipping threshold in order to tip it? And can we go back once we're past it? What does it even look like when we're getting close? These are all questions that scientists are trying to answer with modelling, and so far it doesn't look great. For example, it now seems inevitable that the West Antarctic ice sheet will collapse. But it's very difficult to know what the early warning signs will be and when it will be too late to prevent a system from tipping. The best option is to limit emissions as much as possible to reduce the risk and plan to adapt to those changes that are in store. When it comes to solutions, we have the answers. We need to change the way we do things, which requires policy measures to make more climate-friendly decisions easier and cheaper. In the simplest terms, we need to stop burning fossil fuels and restore natural environments. But don't just take it from me. If you want to hear more about what the world's leading experts say we need to do, I made a video about it up here. But unfortunately, there are a lot of false solutions out there too. Companies have realised that their customers want climate action, and there's a marketing opportunity if they can present their products as environmentally friendly. It means there's a lot of greenwashing about. Lots of products are supposedly carbon neutral nowadays, which may make you feel better about buying them, but are they really carbon neutral? Because if these guys are claiming to have a net zero target, that should definitely be ringing alarm bells. Greenwashing is everywhere, and the number one way to decipher whether a claim of carbon neutrality or a net zero target is worth its salt is to check which emissions it actually covers. They're typically divided into 3 scopes. The first is emissions directly produced by the company, for instance, fuel burned in company cars. The second is emissions generated indirectly by the company's activity, like from generating the electricity used in its buildings. And the third is emissions from its products both up and down the chain. So for fossil fuel companies, the vast majority of their emissions are going to come from burning their product, i.e. scope 3. And can you guess which scope isn't included in their targets? Another false solution that is also often rolled out is CCS, short for carbon capture and storage. The idea of CCS is that we burn the fossil fuel, then capture the carbon and shove it underground somewhere. Sounds like a win-win. But the problem is that there is no way in hell that we're going to be able to do that for all the fossil fuel emissions we currently produce. It's technically and economically impossible. And yet, it's often presented as a get-out-of-jail-free card. There is undeniably a role for CCS in a net zero future, but it's minimal, and it will probably only be used to clean up those emissions that are absolutely impossible to decarbonize. The promise of CCS allows big polluters to get away with continuing to pump filthy emissions into the atmosphere, like your housemate who stacks up the dirty dishes in the sink, saying, "Chill out, I'll do it later, bro." The last kind of false solutions are geoengineering solutions. These range from audacious to downright wacky. On the more sensible end of the spectrum is something like stratospheric aerosol injection, which proposes to cool the atmosphere by spraying tiny particles into the air at aircraft cruising altitudes. And on the wackier end of the spectrum, we've got proposals like space mirrors, pumping water from underneath ice sheets to the surface, or building enormous underwater dams to prevent warm water eroding the West Antarctic ice sheet. Some of these feel very Ministry of the Future. Personally, I feel that although some geoengineering solutions may be less risky than others, we should probably be working first and foremost to address the root cause of the problem, which is emitting greenhouse gases. Geoengineering is what got us into this mess in the first place, so what makes us think that we can geoengineer our way out of it? False solutions are often used by companies, people, or organisations who have an interest in delaying action and keeping things as they are. And some of these folks are what we might call bad actors. And no, I'm not talking Adam Sandler or the horrors of my GCSE drama performance. By bad actors, I mean those who consistently undermine climate science, climate scientists, and climate solutions. In fact, you will probably spot a few in my comments section. It used to be easy to spot bad actors in the climate space, mostly because they deny that climate change was even happening. If you want to see some of the most common arguments used by traditional climate deniers, then check out this video up here that I did debunking those myths with Climate Adam last year. Recently, things have changed. Modern climate denial isn't so much about pretending it's not happening. It's more about pretending it won't have terrible impacts, or that the solutions will be somehow worse than climate change itself. Or in some cases, pretending that the impacts are so bad that there's no point doing anything about it at all. All these arguments tend to use the same techniques to undermine science, summarised by John Cook on Skeptical Science as FLICK. So fake experts, logical fallacies, impossible expectations, cherry picking, and conspiracy theories. Once you hear these categories, you can spot them everywhere in comments seeking to undermine science. Dr. insert name here is an expert who says that climate change isn't real. What they won't tell you is Dr. insert name here has a PhD in a completely unrelated field and just happens to work for the climate denying Heartland Institute. You often see circular logic and non sequiturs like climate has always changed, so current change must be natural. A conclusion that doesn't actually follow from the setup. You know, like a joke with a bad punchline. Just because something happened one way once doesn't mean it's going to happen the same way again. Scientists can't even predict the weather, how can they predict the climate? These arguments suggest that because uncertainty exists, we don't know anything. But as we've seen, uncertainty is inevitable. It doesn't mean we can't see what's going on. In fact, acknowledging uncertainty suggests we have a better understanding of the environment. Plus, we're very good at predicting the weather. If we weren't, no one would even bother with the forecast. Oldest trick in the denier's handbook, this. For example, this year's Arctic sea ice extent was only the 15th lowest on record. Therefore, climate change isn't happening. Single points in a record don't tell us much. It's the trends over the longer term that we need to focus on. Overall, Arctic sea ice has declined by 12 or 13% per decade since the 1970s. Zoom out on the graph, bro. Climate scientists are all in on it because they make hella cash out of it. They want to use net zero to take away our freedoms. It's the World Economic Forum, man. Do you realise how bonkers you sound? It's one step away from chemtrails. If I was being paid by the World Economic Forum, do you think I'd be making YouTube videos from my dining table, which is also in my living room and my office? Nah. The antidote to bad actors is providing good evidence-based information. And that's what I do on this channel. So if you appreciate the work that I do, please like and share these videos and consider supporting the channel on Patreon. I'll put the link below and in the pinned comment. Now, finally, activism. It's all well and good knowing about the science and engaging with good content about the science, but it's what we do with that knowledge that really matters. As a scientist, I'm always going to be bringing the science. Scientifically, there's still lots to discover and lots we don't know, especially in the polar regions. But the science is just the first step. What's more important is taking what we know and turning it into useful action. The scientific evidence is abundantly clear. We need urgent transformational change, and that has to come from us. Some people view activism as a dirty word synonymous with vandalism or obstruction, but activism just means actively being part of the solution, with or without the soup. Activism looks different for different people. For you, it might be getting organised in your local community, talking to neighbours and starting local initiatives. Or it might be signing petitions, writing to your elected officials, or running for office yourself. It might be joining a campaign group, setting up an initiative in your trade union, or going on a demonstration. Or you could engage in non-violent direct action. Personally, I've done pretty much all of these, and I've seen that all of these methods of change are essential. They all play a role in driving forwards our demands for climate action. There's a place for everyone in climate action and room for everyone to play to their strengths. Obviously, for my UK viewers, there is a big election coming up, and I recommend Vote Climate if you want to see which parties have the best policies on climate change in your area, and if you want to let politicians know that voters care about climate change. Voting is just the start, but it's an important place to start. Whatever you do, I urge you to do something. Getting involved in action in whatever flavour works for you is also a great antidote to the despair and fear that can come with regularly engaging with climate change science. And getting together with other people who share the same vision and want to be part of the solution is how we make a better future. So, thanks for watching, and thanks for being part of the first 10K. Here's to many more. That's it for today, but if you can't get enough, then check out this playlist of my favourite videos. Cheers!